everyone. Today we are going to see about P is the projection on a Hilbert space H with range M and null space N. Then M orthogonal to N implies P is the self-adjoint. M orthogonal to N implies P is the self-adjoint, and in the case n equal to m orthogonal, and in the case n equal to m orthogonal. First part we have to take, since P is the projection on the Hilbert space with range and m null space n, which is otherwise known as P is the perpendicular projection of H with range m and null space n. So if it is a perpendicular projection, means it will exist P square equal to P with the range m and the null space. By projection theorem, H equal to m plus n. So what we do means P is the self adjoint in the case n equal to m orthogonal. We have to prove this. Okay. First part we have to prove that P is the self adjoint. So H equal to m plus n. So so the vector m plus n. So the vector Z belongs to H. M plus n P square P of so the vector Z is uniquely expressed as Z equal to x plus y, x belongs to m, y belongs to n. So P of Z equal to x, P of y equal to 0. And if m plus 1, m plus n, then x comma y equal to 0, y comma x equal to 0 for all x belongs to m, y belongs to n. Also if m plus n, then x comma y equal to 0, y comma x equal to 0, x belongs to m, y belongs to n. We have to prove that self adjoint, that is P star equal to P. Okay, P star equal to P. Then P star of adjoint means P star of Z comma Z. So P star of Z comma Z is P star is P, that is we take Z P of Z, P Z equal to x by 1. So Z can be x plus y, x comma x plus y comma x. So P star of Z comma Z equal to x y equal to 0, x comma x. So we get x comma x. P Z comma x is nothing, and P Z is x comma Z, x plus y, x comma x plus x comma y. So x comma y 0, x comma x. From 3 and 4, if we equate both side or x comma x, so P star Z comma Z equal to P of Z comma Z. So P star of Z minus P of Z comma Z equal to 0, P star minus P of Z comma Z equal to 0, P star minus P equal to 0, P star equal to P. P is the self adjoint, we prove. Then we take P is the self adjoint, that is P star equal to P. We have to prove in the case m orthogonal to n, that is xy equal to 0. M orthogonal to n, we take P is a self adjoint, we have to prove that m orthogonal to n. So P is the self adjoint, m orthogonal to n is xy equal to 0. So x comma y equal to x can be written as P of Z, P of x plus P of y. So x comma y, P of x comma y, x P of y equal to 0, it will goes to 0, px comma y. So x comma P star of y, x comma P star equal to P of y, x comma y. So P of y is 0. So x comma 0, which is xy equal to 0. So m orthogonal to n. This condition is proved. Next, what we have to prove means n equal to m orthogonal. So let y belongs to n. Y is belongs to capital N. Y belongs to n means we know that m orthogonal to n. So m orthogonal to n, x belongs to m and y belongs to n. So x comma y equal to 0. So y belongs to, where will y belongs to n. So n is m orthogonal, as m orthogonal to n. So this n is contained in m orthogonal. N is contained, if n is not equal to, now we take n is not equal to m orthogonal, means that null space is contained in m orthogonal. We take that n not equal to m orthogonal, means then it is a proper subset of m orthogonal. So the proper closed, it is a by using a projection theorem, it's a proper closed linear subspace of the Hilbert space M orthogonal. There exists a non-zero vector Z0 belongs to M orthogonal, such that Z0 orthogonal to Z0 belongs to M orthogonal, and Z0 orthogonal to M. N. Z not orthogonal to M. Z not belongs to M orthogonal such that Z not orthogonal to M. Okay, so Z not orthogonal to Z not belongs to M orthogonal, Z not orthogonal to M, and Z not orthogonal to N. So he is a subset. N is the subset, so it is belongs to M orthogonal. There exists a non-zero vector that is N orthogonal to the subset N. Okay, we know that Z not orthogonal to Z not is orthogonal to M orthogonal belongs to N. Z not orthogonal to M and Z not orthogonal to M. So Z not orthogonal to M plus N orthogonal. So Z not orthogonal to H. So we know that only a zero vector is orthogonal to the whole space H, and 0 orthogonal equal to H orthogonal 0. So Z naught must be definitely equal to 0, which gives that the contradiction Z naught is a non-zero vector. So our assumption n not equal to M orthogonal is wrong. So n equal to M orthogonal, in other words, null space of P is perpendicular to the range P, so that P is the null space of P is perpendicular to the range of P, so it is P is the perpendicular projection. Another form of the above theorem is a linear operator P on a Hilbert space H is a perpendicular projection P equal to P square equal to P star. Hope you all understand, and thank you.